How are we doing, guys? Welcome to the video. This is the first video on simple harmonic motion. We're looking at fundamental applied maths, pages 221, 222, questions 2, 5, 8 and 10 in this section. We're going to start off talking about a law called Hooke's law that you would have met for your junior cert. It says if you have a spring of natural length L0 and you extend it by applying a force to a length L, then the force is directly proportional to L minus L0 is called the extension. Okay, so the extension of the spring, directly proportional to, that means you just multiply it by some number, which is called the elastic constant or the spring constant. The elastic constant normally looks something like in question 2 here, it's 9 newtons per meter. That means for every meter you want to extend this spring, you need to apply 9 newtons of force to do that. So that's the rule we're working with today. Question 2 is a very straightforward question. It says a string of natural length 2 meters and elastic constant 9 newtons per meter has that. Okay, find the force on a particle at the end of the string when the length is 3 meters, 5 meters, or 3 1/3 meters. What length of string will have a force of magnitude 54 newtons? So if you have a length 3 meters, then the force is spring constant 9 times 3 minus 2 is 1. So 9 times 1 is, there's a 9 newton restoring force that the string will apply if you stretch it out. Or equivalently, you'll need to apply 9 newtons of force to get there. These two forces are the same size by Newton's first law. The length, and if they're not the same size, the thing is going to start moving. The length is 5 meters. Well, that's again spring constant multiplied by the extension here is 3. 5 minus 2 is 3. So 9 threes are 27 newtons. And the last one, if the length is 3 1/3, the spring constant is still 9. The extension is 3 1/3 minus the natural length of 2, which is 1 1/3. 4 over 3 multiplied by 9 is 12 newtons. When do you get a force of 54 newtons? Well, you say the force there has to be 9 times whatever the length minus the natural length is, okay, times the extension, which means 6 newtons. When you divide across, 54 divided by 9 is 6, is L minus 2, and the length has to be 8 meters. Okay, question 5. Says a particle rests on a smooth horizontal table between two vertical walls which are 35 meters apart. It is attached to the left-hand wall by means of an elastic string of natural length 2, elastic constant 7, and to the other by means of a string of natural length 3, elastic constant 3. Find the position of equilibrium and the two positions where the resultant force in the particle would be of magnitude 40 newtons. So here's our question. Okay, we've got our particle resting on a table. We've got 35 meters between the walls, so if the distance from the left-hand wall is x, then the distance from the right-hand wall is 35 minus x. Here's our natural length and spring constant for one, and natural length and string constant for the other string. And when we're in equilibrium, then the forces to the left and the forces to the right have to be the same. So what's the force to the left when we're a distance x from the left-hand wall? Well, that's going to be 7 times x minus 2. Okay, so our extension is x minus the natural length, and that has to be the same as 3 times 35 minus x minus 3, okay, which can also be written as 3 times 32 minus x. Okay, so to find that value for x, you just solve that. 7x minus 14 has to be the same as 96 minus 3x. Move them both over, you get 10x equals 96 plus 14 is 110, and x equals 10 meters. Okay, so 10 meters, and you'll always say from one of the walls, so I'm going to say from the left-hand wall. When is the resultant force 40? Well, there's two positions. Either force to the left minus force to the right has to be 40. Okay, so you've got a bigger force acting to the left because you've stretched it this way, and this spring is now more stretched. It's going to be trying to pull it back. Or force to the right minus force to the left is is 40. So you've pulled it this way, and now the force to the left is smaller, the force to the right is bigger. It's trying to pull it back that way. So force to the left minus force to the right. So this is a different value, so I'm just going to call it y. Okay, but it's the same principle. If that's y, this is 35 minus y. So force to the left is going to be 7y minus 2. Minus force to the right is going to be 3 times, 35 minus y minus 3. So same thing, 32 minus y. And that has to equal 40 as well. So 7y minus 14 minus 96 plus 3y equals 40. 7y and 3y is 10y minus 110 equals 40. I'm about to run out of space here, so that's 10y is 150. Okay, so my first y is 15 meters. Again, you want to say from the left hand wall. I'm leaving that out. We'll do it over here. We'll do it properly. Force to the right minus force to the left is just the opposite of this. It's this, take away this. You're going to get minus 10y plus 110 when you do that. Okay, so move the 40 to the left hand side and the 10y to the right hand side. You get plus 10y there. You get 70y, or 70, and divide through. So y equals 7 meters again from the left hand wall. Okay, question 8 says a particle of mass 2 kilograms hangs from the ceiling by means of an elastic string of natural length 2 and elastic constant 7. Find the length of the string when it's in equilibrium. Okay, we'll do the second part in a second. So it hangs from the ceiling. Okay, there's the natural length, there's the spring constant. When it's in equilibrium, the upward forces and downward forces are the same. So the upward force is your Hooke's law of force, okay? That is 7 times whatever the length is minus 2. And that has to be equal to your downward force, which is the weight of the particle, 2g, 2 times 9.8. So we get 7L minus 14 equals 19.6. Which means 7L equals 19.6 plus 14, which is 29, 33.6. And then L is 33.6 divided by 7, which will come out as 33.6 divided by 7, 4.8 meters. Okay, so we're hanging 4.8 meters below the ceiling. Part 2 says if the particle is stretched a further distance x, show that the force on the particle is of magnitude 7x. Okay, so we're just going to pull it down some extra distance x here. Okay, so this length of the particle is now L plus x. The length of the string. So the net force acting, then now there's going to be a greater force up. If you let that go, it's going to move upwards. Past its equilibrium point, probably. It's going to jump up past it and start moving up and down in what we call simple harmonic motion. But initially, the upward force is going to be given by Hooke's law, which says it is 7 times the natural length, the length of the spring is L plus x minus the natural length of 2. L is 4.8. 4.8 plus x minus 2 minus the downward force is 19.6. Well, that's 7 times 2.8 plus x minus 19.6, and that's 19.6 plus 7x minus 19.6 is 7x. Okay, so if you extended some distance x, you get the spring constant times x returning. Okay, that's going to be a fairly common feature in questions later on in the chapter. Question 10 says a particle is hung from 2 points P and Q on the same horizontal line where PQ equals 8 meters by means of 2 elastic strings of equal length. The strings have a natural length 2 meters and 1 meters. They have elastic constants 10 newtons per meter and 7 newtons per meter respectively. Show that the angle A which the two strings make with the vertical is given by sine A is 12 over 13 and find the weight of the particle. Okay, they gave you the diagram there. I've got it done more or less again here. There's P and there's Q. We're told those two lengths are the same and those two angles are the same. That length is a common side. These triangles are congruent. So because I know that the distance across here is 8 meters, and they're congruent triangles, these corresponding sides have to be 4 meters each. So what we can do is come along and look at that F1 and resolve it into components. Okay, so F1 is the spring force acting up this way that's keeping this particle, I suppose, where it is, stopping it from dropping under its own weight, which is another force acting. And F1 is resolvable. You can say this part here, the opposite side of our triangle, is F1 sine A, and the upward component of that force is going to be F1 cos A. Same thing over here, that's F2 sine A, and that's F2 cos A. So because this thing is in equilibrium, it's neither moving left nor right, we can say the left and right forces are equal. And that means F1 sine A equals F2 sine A. Sine A's cancel there. F1 and F2 are the same size. Okay, which is kind of necessary for the symmetry in this problem. Well, F1 is going to be the spring constant 10 times whatever that length is minus its natural length 2, and that needs to be the same as F2, which is its spring constant 7 times that same length L minus its natural length, which is 1. So we get 10L minus 20 equals 7L minus 7. That's 10L minus 7L equals 20 minus 7 plus 20 minus 7. 3L is 13, L is 13 over 3. And they've asked us to find the angle A, or the sine of that angle. So let's come back up to this triangle up here. Okay, so we know we've got 4 across the top, and we've got now 13 over 3 along the side. So that angle there, the sine of that angle, sine A, is going to be 4 over 13 over 3. And multiplying top and bottom there by 3, you get 12 over 13, which is what they asked us for. Okay, now if you know your triangles, your right angle triangles, that 12, 13, and if that's A, sine A is 12 over 13, cos A, that's going to be 5 by Pythagoras. Okay, so cos A, which we're going to need in just a second, is 5 over 13. Okay, the other way to do that is say A is the sine inverse of 12 over 13 in your calculator, and then find the cos of your answer. So the next part was find the weight of the particle. Well, again, it's in equilibrium, so we can say the downward forces are equal to the upward forces. Our downward force is the weight, which is what we're trying to find. So they're saying, what is the upward force? Well, it's F1 cos A plus F2 cos A. We know that F1 and F2 are the same size, so we can just say that's twice F1 cos A. And that is 2 times F1 is 7. Oh, excuse me, 10. It doesn't matter which one you use, F1 or F2, they're the same. 10 times L, which we said was 13 over 3, minus 2. And then cos A is 5 over 13. And we'll just save ourselves some time here. If you biff that into a calculator, you get yourself that the weight, or maybe we're not saving any time at all, sorry, the weight of the particle comes out as 17.95 newtons. So I'll leave it there. plenty of other questions for you to look at in the exercise, and I'd very much encourage you to try them. Okay, bye bye.